If you're happy, yes, thank you, Scarlett. I would like to introduce you to the agenda of today, which is the following one. We will have 4 very exciting talks from our PhD student funded through the Research Alliance program. And we will also have 1 Microsoft talk after the first 2 talks from the PhD students. So if we are happy, we can start the event. And as I said, feel free to ask the speakers as many questions as you can have. Hitesh, you want to say something? No, sorry. You just jumped at least on my screen. So I thought, so okay. So otherwise, without further delay, let me introduce you the first speaker. It's Alessandro Ottino. Alessandro is a member of the Optical Network Group at UCL under the supervision of Dr. George Zervas. Pablo Costa is his Microsoft supervisor. His works relate to optical fabric for zero latency memory disaggregation at petabit per second cluster scale networks. And today his talk is about optics for distributed learning, challenges and opportunities. So let's start his pre-recorded talk. And this will be followed by question and answer that Alessandro will take live. So looking forward to the exciting talk. Thank you. Okay, I cannot listen.
I can't either, Francesca.
Let me start again.
Thank you, Scarlett.
Hello, my name is Alessandro Ottino, and I'm a first-year Microsoft-funded PhD student at Optical Networks Group in UCL, under the supervision of Dr. Giorgio Zervas and Dr. Paolo Costa. Today, I will be presenting the main topic of my PhD, which is with regards to optics for distributed learning. I would just like to mention that this work is still in its very early stages, and so I will only be presenting my vision for it. In recent years, the demand for machine learning has exponentially increased. To improve prediction capabilities and allow new applications, deeper and larger models, trained with larger amount of data, are needed, as it can be seen from the graph on the right-hand side of the slide. The issue is that these models are too large to fit on a single accelerator, and if they do, they converge too slowly, making them unsuitable for practical training. The solution to this problem is distributed learning, where the ML workload is distributed onto multiple accelerators. For example, the deepest models shown in the figure on the right-hand side have been trained with at least 512 accelerators. There are 3 main ways to partition a neural network and therefore to perform distributed learning. The first is data parallelism, in which the neural network is copied onto multiple accelerators, and each of the copies is trained using different data, so the data is partitioned. The second is model parallelism, in which the neural network computational graph is partitioned in the intra-layer dimension and distributed onto multiple accelerators. The third is pipelining parallelism, where the graph is partitioned in the interlayer dimension and distributed. There is an additional type of parallelism, which corresponds to any combination of the 3 types previously mentioned, and it is referred to as hybrid parallelism. The number of devices used for each type of parallelism is called partitioning degree. There are 3 main bottlenecks for distributed learning workload. The first is compute, where the training is limited by the computing time of the neural network graph. The second is memory, where the training is limited by the memory transfer time. The third is the network, where the main limiting factor is the communication and data transfer time. When the number of nodes or devices in the network increases, memory and computing bottlenecks can be mitigated through the correct partitioning, and more stress will be put on the network. Therefore, the workload throughput will be limited by the communication time. As it can be seen from the graph on the left-hand side of the slide, when the number of nodes is increased, and especially when the network contains hundreds of nodes, distributed learning workloads suffer large computation and communication time imbalance. Therefore, the time taken to transmit data is significantly larger than the one taken to perform actual neural network computations. One of the reasons for this happening is the current distributed learning networks suffer from rack bandwidth over subscription, and so the communication bandwidth between inter-rack nodes and inter-rack nodes largely differs. This leads to another problem, which is limited partitioning degree in the sense that we cannot expand one degree of parallelism over a certain limit without largely affecting throughput. This is especially true for model parallelism. Another problem that could arise in a certain type of application, such as large model inference, is the latency that comes from the communication protocol and the network packet switches. So, why are we proposing optics for distributed learning? Current distributed learning network topologies are based on electrical packet switching technology. This type of networks have large limitations. One of the main limitations is their scaling out capabilities for constant bandwidth. Studies have shown that with current state-of-the-art technologies, to scale a full factory network to 256 GPUs, each having 2.4 terabit per second bandwidth, 960 MV switches and 9216 MV links would be required, making their scaling unfeasible from the point of view of cost, power, and complexity. Because of this problem, current networks suffer of heterogeneous bandwidth between nodes. In most cases, they have a full I/O connection bandwidth between inter-rack devices and significantly smaller bandwidth for inter-rack connections, leading to the problem discussed in the previous slides. In addition, in some cases, it is not possible to have full device connectivity, depending on the topology used. This largely affects the possible types and degree of parallelism. As an example, on the upper right of the slide, we show the topology used by Google in their TPU pods, which is a 2D torus in which every device has a connectivity limited only to its neighbor. So, how can optics overcome this problem? Through introducing optical circuit switching, we can allow device-to-device communication at high bandwidth due to the high capacity of optical fibers. In addition, there is no distance limitation thanks to low loss and minimum latency, which is mostly limited to the speed of light in the fiber. It was seen that optical circuit switch-based topologies can allow better complexity and cost scaling for high bandwidth. Also, transparent and configurable topologies can be allowed with minimal penalty. The implementation of optics can allow us to scale out over the rack with minimal penalty increase. Therefore, high bandwidth interconnection between device pairs with large number of nodes could be achieved, maintaining still a smaller complexity than electrical packet switch-based topologies. This could allow full degree of freedom application-specific neural network partitioning. If these conditions are met, it would then be possible to maximize the net throughput of the distributed learning workload. In addition, through the implementation of an optical circuit switch topology, the packet processing and switching overhead could be removed. Obviously, there will be some limitation of what optics can achieve, and there are some other issues which might arise. As in any network, it is not feasible to scale indefinitely both number of nodes and bandwidth. Therefore, there will be some trade-off that will be needed to be taken into consideration. My goal is to create a new optical circuit switch-based topology for distributed learning workloads, develop a tailored full degree of freedom partitioning algorithm, and application-aware scheduling algorithm so that we can minimize the training time, maximize the resource utilization, and maximize the throughput. So, how can this be achieved using optical circuit switching? An important property of distributed learning workloads is that their communication pattern is repetitive and predictable, making long-lasting optical circuits a feasible solution. From the analysis of the communication pattern of optimal distributed neural networks, the network requirement can be extrapolated, and from this, a topology can be developed. To show the impact of a given topology on the training time, we can analyze the example of data parallelism's gradient-reduced strategies. As previously mentioned, data parallelism consists of copying the same neural network on multiple devices, where each device has been provided with a different set of training data. For the distributed learning to converge and act as a single neural network, every iteration, the gradients for each parameters of every device needs to be shared with all the other nodes, so that, at the end of the sharing, every neural network has the same set of gradients, which consists of the sum of the gradients of all devices. This process is called gradient reduce. The most used gradient reduce strategy is ring reduce, which requires a ring topology. As seen from the animation on the upper right of the slide, the gradient have been divided in segments equal to the number of devices, and at each time step, a single GPU sends a unique segment to its neighbor. The receiving GPU sums the received segment with the one present in its memory, and at the subsequent time step, it will send it to its neighbor. So, after n-1 steps, every GPU has a full segment containing the total information of the segment of all the GPUs. At this point, a GPU will send their full segment to the subsequent GPU, which will then copy it in its memory. In the subsequent iteration, the recipient's GPU will share the received segment to its neighbor. So, after n-1 steps, all GPUs will receive all the gradients. Another strategy is torus reduce, which requires a 2D torus topology, as seen from the graph on the left. For a large number of GPUs, for example 10,000 GPUs, torus seem to perform a ring reduce in terms of reduced time. However, when we increase the amount of data transmitted from 1 kilobyte to 10 megabytes, we can see that for 10,000 GPUs, ring reduce starts to perform torus reduce. This is even more evident when for gradient sizes of 10 gigabytes. So we can see that the gradient reduce time is largely dependent not only on the topology but also on the application. Using an optical circuit switch based topology, we could theoretically reconfigure the network in any of these topologies, therefore minimizing the reduced time for the relevant application. The following block diagram outlines the elements which need to be developed and completed to achieve my goal. The first step is creating a distributed learning simulator, which is composed of three main blocks: the profiler, the partitioning algorithm, and the communication pattern simulator. The profiler takes as input a neural network and outputs a profiled computational graph, which takes into consideration the forward and backward propagation time of every operation, their corresponding memory access time, and the device I/O capabilities. The profiled graph is then taken as input alongside the number of devices for the partitioning algorithm, which will output then a partitioned neural network. The partition algorithm that needs to be developed should not be limited by any partitioning degree and any current topology. Once a partitioned neural network is obtained, it is used in the communication pattern simulator to understand what are the timing requirements and scheduling pattern for the corresponding network. Once the distributed learning simulator has been developed, multiple neural networks with different architecture and different numbers of nodes will be analyzed, and from the communication pattern, a physical optical circuit switch topology will be created. To do so, we'll take into consideration cost, power, technology, and requirements for future implementation. Once a physical topology has been created from the information given by the distributed learning simulator, a logical topology based on the physical one and the current network will be created, and this information plus the communication pattern will be used to create a custom circuit switching scheduler. This will be application aware and therefore tailored to the specific job or multiple jobs to be completed in the network. Once this is all done, from the neural network partitioning and availability information, we can create a device placement algorithm to actually deploy and train our partitioned neural network. In conclusion, we have seen that optics could be a suitable solution for the scaling of distributed learning workloads and could maximize the net throughput, minimize the training time, and maximize the resource utilization. It could also allow the training of machine learning models with more than 1 trillion parameters using existing algorithm and neural network architecture, thing that is not feasible at the moment due to the extremely large convergence time. In addition, using the proposed approach, we could achieve faster hyperparameter tuning and faster model evaluation, leaving data scientists more freedom to explore different designs. I am aware that the proposed approach is very challenging and requires a lot of work. However, I am confident that this is the correct direction to explore, and I am happy to have the opportunity to face this challenge. Thank you all very much for listening.
Thank you very much, Alessandro, for your very nice talk. I think the talk now is open for questions. If you have any, feel free to write them in the meeting chat or raise your hand so that you can talk directly to Alessandro. So as we wait for questions to come in, maybe I could start with one. Alessandro, you were talking in your talk about trade-offs.
Yes.
Using this optical circuit switch that you are proposing. Maybe I miss it, but did you talk about the trade-off? Could you comment on them?
The thing is that every type of topology will have some limitations. The thing is that we still do not have enough data to understand which trade-off should be done in case, because we cannot, it is extremely unlikely that a perfect topology can be created with extreme scaling and unlimited bandwidth. So we have to see, depending on what the simulator will give us, which trade-off we should take into consideration for actual implementation.
Okay, yeah. Yeah, I see Fotini Carino has raised their hand. So Fotini, please. Fotini is from Microsoft. Fotini?
Fotini is muted.
Sorry, I was muted. Sorry, Alessandro, very nice presentation. Thank you very much. I wanted to ask you about what is the target latency that you are aiming at for distributed learning workloads.
Thank you for the question. In most cases, for distributed training, especially training purposes, latency is not so much of a big requirements. What is mostly needed is faster configuration more than anything. But in any case, if I could have, in cases I want to expand my topologies for optical inference, in that case, the latency that I'm looking for is less than tens of microseconds between devices. If not, the inference time would be too large to be used in practical applications.
And if I may have a follow-up question, do you plan your simulator to take into account to quantify the impact on the performance?
Yes, that's the whole point. My simulator will take into account the impact of performance. The whole point of the simulator is trying to create the best partitioning method to maximize the performance and resource utilization together.
Thank you.
Thank you. I believe next is Hitesh Balani from Microsoft, please.
Hi, Alessandro, great talk. So one minor question and a possible discussion point. So minor question is, at the moment, are you focusing on training or inference or both?
Thank you for the question, Hitesh. Right now, I'm focusing mostly on training because this is the main limitation that we found. Main limitation that we're finding for developing really large models. For example, there are multiple groups that are working on distributed learning for extremely large model. For example, Microsoft has AI at scale, which their focus is maximizing the training, minimizing the training time of extremely large models. So for now, I'm focusing on to the training. Then maybe I will focus on inferring. I think that these two could be different topologies and different networks. They can be separated because they would have different patterns and they would have different requirements.
Sounds very helpful. Francesca, can I make the discussion point, or are there other people waiting?
There are other people, but we have time, so please go ahead.
So as you think about the PhD topics, it sounds very, very interesting and timely. It would be good for you to think about, I think at the moment it seems like the focus is on topology and the partitioning methods. Maybe there's an opportunity of co-designing these techniques with the actual ML algorithm and perhaps with the underlying optics. Maybe that's something that you've already thought about, or maybe those opportunities don't exist, but maybe worth thinking a little bit about.
What I'm thinking is that it is actually doing this co-optimization. So trying to create a feedback loop, saying first I want to create what topology can optimize what I have, what is theoretically possible, finding what is the theoretical limit for the best neural network partitioning, and from there try to say what is the topology that goes similar, that creates the minimum penalty for that type of training. And from them on, create a feedback loop that modifies my net partitioning algorithm. So it's a co-optimization, which it's created even more complicated. It becomes even more complicated when I consider multiple jobs and scheduling, and it's a lot of things that need to interact with each other, and I cannot consider them extremely independent. They have always to consider them together.
But
thank you.
But just to follow up, because I think if I understood Hitesh's question is also potentially also changing the actual training algorithm. And I think, Alessandro, this is something that you already start doing, for example, in your broadcast reduce. So effectively, you are actually looking also how you can modify the training algorithm, moving away from the ring reduce to take advantage of the new topologies and the new flexibility. I think this is where you were.
Yeah,
you were going.
Very interesting, fascinating. Thank you. That was helpful. So, thank you. Thanks, Alessandro.
Thank you.
Excellent. I saw before there was a raised hand, but it was lowered. Was intentional, right?
Yeah, that was me. I think my question was covered by Hitesh and Pablo discussion.
Okay, excellent. I guess that. All right. Any other question that you would like to ask to Alessandro? Okay, so I think if there are no further questions, then we can move on to the second talk. Alessandro, just want to ask you, in case there are new questions appearing in the meeting chat, I would really appreciate if you could answer them live whenever you had the chance. Otherwise,
obviously, yes. Thank you so much.
Otherwise, thank you very much for your very, very interesting talk. So I would like then to, I would like to start to introduce the second talk. So the second speaker of today is Carrie Clark. So Carrie is a member as well of the Optical Networks group at UCL under the supervision of Dr. Jixin Liu. Hitesh Ballani and Paolo Costa are his Microsoft supervisors. And I would say compared to all the other PhD students that we have invited so far at the event, Carrie is at the very end of his PhD. If I'm not mistaken, he's finishing his writing up. So exciting time and bit stressful time for him, but we have invited him actually to give a talk, as we believe as we believe he's an excellent example of a successful research alliance collaboration, as well as a very successful PhD student. So he had an extended 9 months internship with us back in 2016, working actually on the initial design and prototypes of phase caching. And our joint collaboration with him and the team led, among other things, to work published on actually this month's issues of Nature Electronics. So many congratulations. He also has been awarded several awards. For example, the top prize in the prestigious EPSRC Connected Nation Pioneers competition in 2018 and won the bronze in engineering at STEM for Britain 2019, which was held at the House of Parliament. So today, Carrie will be talking about synchronous sub-nanosecond clock and data recovery for optical switch data centers using clock phase caching. So let's start the pre-recorded talk, and Carrie will be with us to answer any question that you may have. Thank you.
Hi, my name is Carrie Clark, and I'm a completing PhD student from the Optical Networks group at University College London. The topic of this talk is clock phase caching, a synchronization technique for achieving sub-nanosecond clock and data recovery time in data center optical switches. The work presented in this talk forms the core of our just published in June Nature Electronics journal paper, which is the final end result of 4 long years of hard work and collaboration between UCL and Microsoft as part of the Optics for the Cloud program. So let's begin. Why would you want to use optical switching in the data center? If we look at the challenges for future data center design, one of the biggest is that the rate of data exchanged between servers is increasing rapidly, doubling approximately every 12 to 18 months. Unfortunately, the future scalability of electronic switches that we currently use to interconnect servers within data centers is limited, which ultimately comes from physical scalability limitations of silicon transistors. A future-proof alternative to this is to use optical switches, such as the optical switch shown in this diagram, which transmit data through momentary direct light paths between servers or top-of-rack switches, rather than requiring data to travel through a deep hierarchy of electronic switches. But optical switches need to handle actual data center traffic, so what exactly do those look like? To understand that, we analyzed traffic patterns from a production cloud data center, and we found that many of these traces were dominated by lots of small packets. For example, in this traffic pattern, 99.7% of packets are under 576 bytes. Furthermore, over 25% of packets were 64 bytes or less. To put this into perspective, a 64-byte packet transmits at 25 gigabits per second in only 20 nanoseconds. The impact of this is that optical switches need to be fast to handle small packets efficiently. In order to be able to do that, optical switches need to be able to reconfigure as quickly as possible. Optical switching technologies are out there that can achieve 1 nanosecond switching time, but receivers also need to recover the clock of incoming data before that data can be read. This process is called clock and data recovery time, or CDR locking time. For commercial transceivers, clock and data recovery takes at least 100 nanoseconds, and even with the very best state-of-the-art research prototypes, 8 nanoseconds is still required to recover the clock. Because data center traffic patterns contain many small packets, high clock recovery time impacts overall network throughput for optical switches. To assess more precisely the impact of clock and data recovery time on optical switch throughput, we put our real data center traffic pattern through a comprehensive network simulator. With commercial clock recovery circuits with clock recovery times of over 100 nanoseconds, as shown in this plot, we found that the throughput of the optical switch is under 20 nanoseconds, under 20%. Even with the very best traditional state-of-the-art clock recovery circuits with a clock recovery time of 8 nanoseconds, we found that the throughput of the optical switch is still only 66%. If, however, we reduce the clock recovery time to sub-nanoseconds, we can bring the overall throughput of the optical switch up to 90%, which would allow the full benefits of optical switches to be realized. But the clock recovery process could leverage the unique properties of optical switches that are in data centers. Optical switches are a special case. They require synchronization in order to avoid collisions between packets arriving from different transmitters. With frequency synchronization in place, the problem of clock and data recovery is reduced to a phase extraction process. However, even with that in place, it can still take over 40 nanoseconds to recover the clock phase, as I'll go back to later in the talk. But between any transmitter to receiver pair, the clock phase difference only changes very slowly with temperature, which we could store or cache. We call this technique clock phase caching, and I will shortly show that we can use this to reduce clock recovery time to sub-nanosecond with this technique. If we go back to that core data center optical switch, this is what this might look like. Let's consider that switch. It interconnects all of n by n racks within a data center, where n could potentially be 10,000. Firstly, we synchronize frequency by distributed synchronization, so all those racks have the same clock frequency. Secondly, we synchronize the clock phase of all of the racks connected to the optical switch using clock phase caching. And this is the architecture that we've proposed to do this, which I'll now explain in greater detail. What is clock phase caching? So this is a technique that ensures that the clock phase of packets incoming at any given receiver are the same irrespective of origin. So several things. Firstly, this relies on some sort of clock source, say a distributed one, which synchronizes all of the various transmitters and receivers connected to the optical switch in frequency. Every transmitter stores a cache of phase values that correspond to every receiver that each transmitter can communicate with through the optical switch. Every transmitter also has a phase interpolator so that it can choose any arbitrary clock phase for packets leaving the transmitter. Every receiver has a phase offset measurement circuit that can measure the clock phase offset between incoming data and its own reference clock. Whenever a transmitter communicates with a given receiver, the clock phase of outgoing packets is shifted to align with that receiver's clock. When the packet arrives at the receiver, a small clock phase offset may still remain due to changes in fiber temperature since the last communication from that transmitter or the last clock phase update. This smaller offset is communicated back to the transmitter through either a control plane or through an opposite direction link. This offset is then used to alter the clock phase cached value at the transmitter so that can be used for the next transmission with that particular receiver. The same process occurs for all transmitters connected to the optical switch. For instance, if we now consider a transmitter 1, if that transmitter then communicates with this receiver, it shifts its clock phase to align before sending it. The receiver then measures that small phase offset that remains. That phase offset is sent back to the transmitter, and that's used after correction for the next transmission of data. To show that the concept of clock phase caching works, we built a proof of concept experiment. This consists of two transmitting nodes, a single receiving node, and a central clock distribution unit used to frequency synchronize all three of the nodes. The clock is distributed directly to transmitter 2 Transmitter 1 and 2 send interleaved data packets into a 2x1 Mach-Zehnder based optical switch. The output of that optical switch then passes through a further 2 kilometers of optical fiber before reaching the receiver node. The receiver node receives packets in real time from the optical switch and measures the clock phase from each transmitter at a user configurable rate. The phase offset updates are sent back to transmitter 1 and 2 through a reverse direction link. The 2 by 2 kilometers of fiber are chosen to emulate the worst case round trip clock path that could occur for nodes connected to an optical switch. They are contained within a thermally controlled chamber in order to subject the fiber to a rapid temperature change, emulating worst case data center temperature variation. In our first result, we assessed the impact of different clock phase offsets on the CDR locking time. Shown here is a plot of transmitter to receiver clock phase offset against the CDR locking time. We observed that the CDR locking time quickly degrades to greater than 40 nanoseconds. The clock phase offsets beyond plus or minus 0.1 symbols. The impact of this is that frequency synchronization is not enough because random phase offsets would occur between different transmitters and receivers, and some of those are associated with very long locking times. So we need phase synchronization as well through clock phase caching. Before moving on to my further results, which begin to involve rate of change of temperature, I need to introduce a key property of optical fiber that's very important for clock phase caching. And that is that as temperature changes along a fiber, the delay through that fiber changes. That causes the clock phase values to shift. And we need to use clock phase updates in order to correct for that physical effect. The change in the time of flight through optical fiber due to its thermal sensitivity is given by the multiplication of the fiber thermal coefficient of delay, which is approximately 40 picoseconds per kilometer per degree C for standard single mode fiber, by L, which is the length of the fiber, and by delta T, which is the change in temperature. This change in time of flight arises from a combination of two effects: the physical elongation of a fiber, which is a relatively small effect, and the refractive index change of a fiber with temperature, which is a much larger effect. So back to results. In our second, we measured the long-term stability of our technique. We allowed the 2 by 2 kilometers of fiber to be subjected to random environmental temperature fluctuation for a 2-day period, which can be seen in the plot shown. We also included a period where we turned the air conditioner off and turned it back on again during that time. With clock phase caching running, the CDR locking time was under 625 picoseconds throughout, and no errors were recorded. When we ran the same test with clock phase caching disabled, we observed loss of phase alignment within 2 minutes, resulting in CDR locking time degradation due to clock phase shift. Now, looking at rapid temperature change is the next thing we investigated, and to do this, we subjected the 2 by 2 kilometers of fiber to a 0.11 degree per second temperature change within our thermally controlled chamber. This rate is over 3 times the worst case cloud data center rate of temperature shift that we measured over 228 days of 0.03 degrees C per second. With clock phase caching running throughout at an update rate of 10 Hz, we observed a consistent CDR locking time of under 0.625 nanoseconds with no errors recorded. Upon repeating the experiment with clock phase caching turned off during the rapid temperature rise, we observed degradation of CDR locking time to more than 40 nanoseconds within a second. To further explore the tolerance of clock phase caching to temperature change, we then evaluated the CDR locking time as a function of rate of change of temperature for 4 kilometers total of clock and data fiber, which is the worst case length that you'd see in an intra-data center environment. After evaluating many different phase update rates, we found that the minimum required rate of clock phase updates is strongly proportional to the rate of change of temperature. We can also generalize this result to give the minimum required rate of clock phase updates per unit rate of temperature change per unit fiber length. This is because the change in delay through a fiber due to temperature change is proportional to its length, as we explored on a few slides previous. If we specifically look at the worst case rate of change of temperature within a data center environment that we measured of 0.02 degrees C per second, the minimum required rate of clock phase updates per unit length of fiber is only 0.2 Hz per kilometer, so very slow. An additional important question for clock phase caching is its ability to tolerate jitter in the clock. To assess that, we injected jitter into the clock source used in our experiment. We investigated two cases. Firstly, sinusoidal jitter. We found that the CDR locking time is sub-nanosecond until 0.09 symbols of sinusoidal jitter was injected. Secondly, we investigated Gaussian jitter, and we found that the CDR locking time is sub-nanosecond up until 0.135 symbols of jitter is injected. This tolerance is much larger than typical jitter values for commercial clock sources that could be used for clock synchronization in a data center environment, which are on the order of 0.01 symbols. Of course, to be practical, clock phase caching must be scalable to support many nodes. Clock phase caching does introduce a small overhead on throughput. When an update of clock phase takes place, a receiver might be forced to receive a packet from a transmitter that is only used to update the phase and not used to receive data. This overhead can be calculated by multiplying together the number of endpoints or nodes in the system by the time taken to complete one update, which is short, only 2.08 microseconds, by the required rate of updates per kilometer of fiber to cope with that worst case rate of data center temperature change, which, as we showed, was only 0.2 hertz per kilometer, by the worst case distance between the servers and switches or nodes. The additional factor of 2 here is present because the total length of fiber contributing to phase shift due to temperature is twice the distance between the endpoints. Upon evaluating the worst case overhead, we found that at all typical intra-data center length scales, the throughput overhead for updates is still small. In the worst case of 2 kilometers of fiber between endpoints and 10,000 nodes connected to the optical switch, the overhead is only 1.6%. The impact of that is that clock phase caching is highly scalable. Now, just to conclude, sub-nanosecond clock and data recovery time is crucial for enabling the full throughput of optical switches to be utilized. Our technique, clock phase caching, achieves sub-nanosecond clock and data recovery time in a data center environment. We demonstrate that our technique is stable over 48 hours of real-time operation, that it is tolerant to clock jitter, that it is tolerant to worst-case data center rates of change of temperature, and that it is highly scalable to large port count optical switches. If you'd like to read the paper, I've put a link here directly to the Nature Electronics journal paper. Thanks for listening.
Thank you very much, Carrie, for Thank you very much, Carrie, for the extremely nice talk. Now the talk is open for questions. Feel free to write it in the meeting chat or raise your hand. So as we wait for questions, maybe I could start, Carrie. My understanding is still with this technique, you required some clock phase update. Is that correct?
Yeah, that's correct.
Yeah, I wonder, would it be helpful? So the main reason is because you use single mode fiber and the refractive index, as you very nicely explained, changes with temperature. Would it be helpful, furthermore helpful, to use hollow core fibers or fibers that are less sensitive to temperature? Would it help?
Yeah, absolutely. For every so say if you use hollow core fiber, hollow core fiber's got a thermal sensitivity of about 2 picoseconds per kilometer per Kelvin. Compared to SMF, that's about 20 times smaller. So the rate of phase updates you need is 20 times less. So it is absolutely helpful. But of course, there's do you use hollow core might be more expensive in the data center scenario versus the low cost of SMF, but that may change with time. I do have another paper that explores the use of hollow core fiber in a synchronous system as well, which is potentially worth reading for those that are interested.
Okay, so your point is it may have some advantages, but the higher cost of hollow core could be the main issue, right?
It could be. But it could also be very helpful. That's my assessment.
Yep. Thank you. So we have a raised hand from Nicola Calabretta. As you introduce you, could I ask Nicola to introduce yourself and mention your affiliation, please? Thank you.
Yeah, good afternoon. First of all, I would like to congratulate on the talk. Very, very nice. Yeah. Okay, I'm Nicola Calabretta from Technical University of Eindhoven. And my question is about have you tried to see variation of the input power? Because typically in the clock data recovery, you also have a kind of AGC, kind of automatic gain control. Because probably, have you tried it to see how much robust is to this?
So we considered that as sort of a separate issue almost. So I think you need a similar technique, or could use a similar technique in that case, where you cache the AGC values.
Okay, so you say to also the transceiver, not only the phase, but also the amplitude.
Yeah, so in our particular case, we don't have any control over the AGC in Xilinx FPGAs at all. It would have been amazing to do that, but yeah,
indeed.
at this stage.
But
nice. Yeah, it's an excellent point.
Yeah, another question is that this kind of caching, how much time they take the interpolator when you change from a packet to another?
So in our particular FPGAs, it takes about 2 nanoseconds to do, but it's only due to the particular control circuit that's inside the FPGA.
Okay, so you say if you do this in an ASIC, probably you can do even better.
Yeah, much better. I think that should definitely be sub nanoseconds, as long as everything's aligned correctly.
Thank you. Thank you. Nice, it's great work. Yeah, this nice to have this distribution and this clock. And what is interesting indeed will be actually what is the impact on the controlling the full switch, how much time it takes. Still, this is still the majority probably of the time, but already solving the synchronization is an important point. Thank you very much. Very nice talk. Very nice.
Yeah, thank you.
Francesca, can I just follow up on the Nicola's question?
Yes, please. Thank you.
Yeah, no, actually, Nicola, thanks also for your question. Yes, as Carrie was mentioning, what you can do is that you can apply also for the power, like a similar idea. For example, it's something that we also explore in the context of Sirius, where effectively, since you know the node you're communicating to or you're receiving from, you can also adjust your power accordingly. And in a sense, also goes back to the point we were making yesterday about that, you know, if you also know the next, you have this notion of deterministic schedule, you can also, for example, doing some of the pipelining, so you can mask, you can hide some of the latency associated to change the phase interpolation by basically starting in advance because you know what's coming up next. And,
yeah, okay, yeah. That's a very good point. Yeah, indeed. The point of the amplitude is a bit more tricky because going through a network is always a bit more complicating, aging, connector, cleaning. So
yeah, but the fact is
stuff.
Yeah, but the fact is that you can actually monitor this, so it doesn't change. You know, since the idea is that, you know, since every, let's say, like, you know, few hundreds of microseconds, you talk to everyone, say a few tens of microseconds. What you can do is that you can keep monitoring and adapt accordingly. The same way like Carrie presented that here, just in the phase. Yeah. So that's one of the advantages. That yes, it changes, but relatively slowly.
Yeah, and about the control, you want to comment on this? On controlling the switch, because then the synchronization is good, but what about the controlling the switch? How fast you can control it?
Well, it depends on the technology, because for example, in our case, the switch is passive. So everything you do at the endpoint, because the core of the network is passive. So you don't need to synchronize or control the core, because everything happens at the endpoint. Of course, if you use different technology, that would also change. But in the specific case of Sirius, everything is endpoint only.
Okay, thank you very much, Paul.
Thanks.
Thank you. I think Thomas Karagiannis has a question. Please go ahead.
Thanks, Francesca. Thank you, Carrie. Very nice talk, and congratulations on the publication. I have a very quick question. Do you make any assumptions?
Sorry, Thomas, can you say where you're coming from, just
Oh,
so that everybody...
Yeah, sorry, I'm from Microsoft Research in Cambridge. Very quick question. Do you make any assumptions about the CDR circuits that you're using? Or kind of to put it another way, how specific is to the Sirius architecture?
So I think it depends on what sort of CDR you have available. So in this particular case, you need a CDR that takes a reference clock, and which you can then apply some sort of phase shift on top of. With some CDR technologies, for instance, ones that are reference clockless, the CDR is just locking onto whatever data it gets. So you don't have that like coarse you don't have a frequency already in place. So not specific to Sirius perhaps, but certainly I think digital phase interpolators is what this technique's primarily aimed at, but those are also very widely commercially used.
Thank you, Carrie.
Thank you. I see another raised hand. Paolo has a question. Please go ahead.
Yeah, if I still have 1 minute, Carrie, I want to ask you like a non-technical question, because as Francesca was saying,
yeah, sure.
you're at the end of your PhD, so you are the most senior probably PhD student on the line, and also a very successful one. And I know there are some very young PhD students. So what kind of advice you would like to give to junior PhDs? Like, things that you think, oh, I wish I knew this thing when I started, or any goals, or anything, you want to say. Because I think that would be something useful to hear.
The main thing for me is I remember when I was a junior PhD student, I was really at times quite panicked as to how am I going to contribute? How am I going to find something new? And I think what I would really recommend to anyone starting out is like just the words, it will be okay. You will find something, you will manage to publish. It will take some time. Don't expect to like immediately become fluent in everything. You will get there. I think that's what I would say to anyone junior now.
Thanks, Kai. I think that's a very good suggestion. Thanks. And I would say every PhD student that is on the line, I mean, please feel free, to ask questions either during this event, or also maybe to reach out to like the individual people. Like I'm sure Carrie would be happy to answer both technical and non-technical questions.
Absolutely.
Thank you for your wise words, Carrie.
It's been hard work at times. I won't lie.
I think at this time of this period has been a quite hard period, especially for very early on PhD students. So yeah, definitely it's good to reach out if you can.
Yeah.
Yeah. Do we have any other questions, technical and not technical, for Carrie? I don't see any further questions. However, if anyone would like to ask him something else while I move on, please feel free to use the meeting chat, or obviously reach out to him to ask any further question. But for the time being, I would like to thank you once more, Carrie, for your excellent talk. Thank you very much. And then I would like to move on to the third talk of today. So then, thank you very much, Carrie. So the next talk is a Microsoft talk, and it will be given by Pablo Wilke-Beringer. Actually, the reason we selected this talk is twofold. On one side, we would like to give you an update on the optical storage, as we did yesterday for the optical networking. On the other side, we really believe this is a great example of a successful interdisciplinary research that we carry out in our lab, and we would like to share it with you. And I hope this was also a key message that you took away yesterday, both from Hitesh and Paulo's talk. At Microsoft, we really truly value and work a cross-layered approach, and this is only possible with an interdisciplinary team that we believe we have at Microsoft. So Pablo's talk is one of our great example of how research from one field can have a positive impact on another, and in Pablo's specific case, how his experience in digital signal processing for optical communication has been really successfully applied to optical storage problems. So Pablo joined Microsoft as an intern last summer to work on the performance and complexity analysis of the digital signal processing at the receiver side in Project Sirius. He joined Project Silica this summer after 7 years working on optical communications at the Fraunhofer HHI Institute in Berlin. The title of his talk is Optical Storage Meets Optical Communication and How Digital Signal Processing Can Improve Reading Data Stored in Glass. So this talk as well has been pre-recorded, but obviously Pablo will be here for any questions that you may have afterwards. So let's listen to the talk. Thank you.
Good afternoon, everyone, and welcome to my presentation within the Optics for the Cloud PhD event. I'm Pablo, and in my talk today, I want to illustrate how we can benefit from transferring knowledge between two neighboring fields, in this case, from optical communication to optical storage systems. In particular, I'll be showing the impact of applying digital signal processing techniques common in optical communication to our long-term data storage project called Silica. In yesterday's session, Hitesh already gave a very good overview of what Project Silica is about. With cloud storage rapidly expanding, the target is to disrupt the way we approach long-term storage for cloud applications, which is currently based on magnetic media. With the degradation of such media over time, it is necessary to perform reoccurring rereads and rewrites, resulting in a significant maintenance cost. In Silica, however, data is stored within glass plates, as the one depicted here. This material is robust against radiation, heat, or magnetic stress on its surface, as we have seen in the tests shown yesterday by Hitesh. This makes the medium suitable for very long-term storage. Microsoft picked up this technology in 2017, which at the right side makes use of femtosecond lasers for writing microscopic patterns into glass plates. At the read side of things, we use optical polarization microscopy and advanced post-processing techniques to recover the data. Some of these aspects I will be able to share with you today. Throughout the presentation, we will look into the basics of the write and the read process of Silica and how data is actually stored in the glass plates. We will continue seeing which types of distortions exist and how they are similar to some seen in optical communication. As a result, we will look at some compensation methods from such field, and I will conclude my talk with a summary. Let's start with how data is stored in our glass plates. We start with a glass plate and use a polarized femtosecond laser to create microscopic discontinuities in the medium. As we write along all three dimensions, here only two are shown, we fill a large part of the glass with such discontinuities that we call voxels. Here you see a set of 4 voxels when looking at them from the side. The color of each of these voxels indicates a different set of bits encoded to them. The way these bits are actually encoded becomes a little clearer as we look at the top of these voxels. Now, these are only sketches, but what the femtosecond laser basically does is create microscopic birefringent elements with a certain orientation, which depends on the polarization of the femtosecond laser. Depending on the orientation, we have encoded different bits. So after such data is written into the glass or sent into it, we wait, since after all, storage can be understood as communication not over space, but over time. For our research purposes in the lab, we usually do not have to wait for too long. but the idea is still that these glass plates can rest for as long as potentially many years until a customer wants his or her data back. At this point in time, we illuminate the voxels again with polarized light and inspect its polarization after it propagated through the birefringent elements. Given the scope of the event, I hope that you're familiar with the Poincare sphere, since I will be using it to explain the basic idea of our read process. If you're unfamiliar with it, I think for our purposes it will be enough to know that it is helpful for understanding and representing the states of polarization of light, where the North Pole corresponds to right-hand circularly polarized light and the South Pole to left-hand circularly polarized light. The equator holds all the points that are linearly polarized light. For the readout process, what we will be using is right-hand circularly polarized light on the North Pole shining through the voxels. As such light propagates through a birefringent element, the polarization of light becomes more elliptical depending on the orientation of our voxels. So, depending on the orientation, this initial state of polarization moves on the surface of the Poincare sphere and drops towards the equator on different paths depending on the orientation. For simplicity, in this example, I've been showing only 4 states of polarization, but it's easy to imagine that this concept can be expanded to use fewer or more states, such as in the following example, 8 states. Now, I have to point out that each of these voxels is only a very weak birefringent element, and that the retardance, which is a quantity that tells us how much the shift is from one polarization state to another one because of a birefringent element, introduced by every voxel is only very small. As a result, all of these states end up being squeezed together at the top of the Poincare sphere. Next, what we will be looking at is at this Poincare sphere from the top. And this object here illustrates a camera looking on top of the Poincare sphere, where the top of the camera is aligned with the S2 state of the Stokes space. In doing so, I think it's clearly visible that these states end up being aligned on a circle. For those of you who have worked in any type of coherent communication, radio or optical, this will look very similar to the modulation format called phase shift keying or PSK, where we also place our states on a circle but in the complex plane. So far, we've only seen sketches of our signal, but when we measure these states of polarization in the lab and map them to the complex plane, what we get is something that looks like a somewhat noisy and distorted constellation. It has a slight rotation, slightly deviates from the targeted points, has a wrong scaling, some noise or also interference between neighboring voxels due to optical imaging or other filter effects. I think at this point you get the idea that if we were to have similar distortions, we would probably be able to apply compensation concepts from the field, for example, from optical communication. In the next slides, I want to give you an idea of how the distortions in our system look like, and that they are somehow similar to some of the distortions seen in optical communication systems. In order to do so, let's go back to the side view of our voxels as before, now with 8 different colors since we have 8 different states. When we look at it again from the top, we will see basically a pixel map where each color corresponds to a different state of voxel. Of course, now we usually have many more than these 6 by 7 pixels, so we get much larger maps. And this map can be interpreted looking at the glass from the top, and then every single pixel corresponding to a voxel. Usually we have multiple layers, but for the purpose of this talk, we will just be looking at one layer. What we will be then looking is at the constellation, either for the entire map or for just subsections. So we might be cutting out a certain amount of voxels and look at their constellation. Since it will be a measurement, there will be some distortions and noise, so it won't be perfectly aligned circles, but somewhat off. And then what we will be doing is slide this window across the map of our voxels and look at how these constellations evolve. What we see now here is the same map with a slightly different color scheme, but still the same idea, and many more voxels. We see a rectangle cutting out a few of the voxels and displaying them on the right as a constellation. We can first observe that this constellation is not perfectly circular, but slightly elliptical, having a distortion or imbalance between these two main axes. If we now slide our window across our sector from left to right, we can see that this elliptical imbalance actually changes as we go across the sector. So just from looking at these reconstructed states of polarization directly, we can see that there are some type of spatially dependent imbalances, and maybe not ideally from this illustration, but also some rotations will be clearer to see later on. We can also expect some amount of intervoxel interference from all filtering and imaging effects. Next, we will be looking at the application of different types of compensations, for example, for the imbalances we just observed, which some of you will probably know from coherent optical communication. Also, we will interpret the intervoxel interference as intersymbol interference and apply an equalizer to mitigate the interference. But let's continue step by step. We will start with the same animation as before, but scaled down, since we will need space for the comparison to the other constellations after each of the compensation blocks. As before, we get this constellation directly from the reconstructed states of polarization. For each of the upcoming constellation, we will also look at the standard deviation of the angles away from the centers of mass, where a small angle will correspond to a better defined state and therefore less errors. In the first step, we can compensate the imbalances between the axes, which will fix all the states on the expected circles. We can see that the variation over space is now less visible and the angular standard deviation is slightly reduced. However, our 8 states are not yet all too well defined, which to some extent we can attribute to intervoxel interference. Therefore, since all points can be expected to lie in a circle now, we can use an adaptive equalizer with a constant modulus algorithm, CMA, as an update criterion, which significantly improves our signal. This adaptive equalizer performs a two-dimensional convolution whose coefficients are updated as it slides along the sector. We see a very good improvement not only in the constellation, but also in the angular standard deviation. Furthermore, if we look very close, we may see that this constellation not only shows a fixed rotation, but also a varying rotation across the sector. Similar distortions resulting from phase noise and frequency offsets are very well known in optical communication systems, and a variety of compensators exist. In this case, we use the Viterbi-Viterbi algorithm to compensate for such rotations and fix the constellation, which further improves the overall performance and reduces the standard deviation to 4 degrees. Overall, the application of known algorithms from optical communication reduced our angular standard deviation by a factor of close to 2, which in terms of symbol error rate yielded a huge improvement by a factor of 16. With this, I've come to the end of my presentation, so let's see how we can summarize what we have seen. I hope I got across that storage is basically communication over time rather than space, which makes it possible to interpret certain parts of optical storage technologies, such as Silica, as an optical communication system. We have seen that this allows to directly apply well-understood methods for compensation and analysis from one field in another one, which does not only improve performance, but also helps in understanding the underlying problem and properties of our system. Overall, I can also say that this is not the only example for interdisciplinary work within the project, which already consists of a very diverse team with different backgrounds in computer science, physics, mechanical engineering, signal and/or image processing, and machine learning. And I'm sure I've forgotten a few, but at least for these ones, I know it's true. With this being said, I want to say thank you for your attention and thank you to all my colleagues for their help in getting started in this new environment. If you have any questions, we should be available in the following live Q&A session.
Thank you very much, Pablo, for the very nice talk and excellent example of interdisciplinary team and effort to solve problems. So we have a question from Heidi. I cannot see the affiliation, so the question is, why do you analyze S1, S2 similarly to I and Q imbalance per vertical slice? Is there a physical reason why vertical slices work better than horizontal? Thank you. The question is from Eindhoven University of Technology. Thank you.
I see. Yeah. I think I can take this question. I would say generally, I mean, for this presentation, it was, I think, very easy or very illustrative that we can just start at the top of the Poincare sphere and then just drop down, which just gives us slices across, horizontal slices of the Poincare sphere. Generally, if you could, start at a different point and have a different birefringent elements, we could also point or position our points on a different slice of our Poincare sphere. But this is how it's done at the moment. And yeah. Does that answer your question, Heidi? Oh, there's another one.
Yeah, there is similar question regarding the equalizer. Is that 2D in space or 1D across the vertical slices?
I see. Let me see if I understand it correctly. So it's 2D in space. Yeah, it's 2D in space. So it's groups of voxels that are in space are closely, neighboring voxels. So roughly a few voxels usually might contribute to the output of a single voxel. So the equalizer is similar to a 1D problem in communication systems. Instead of having a fixed window size, it's now more of a 2D patch size that is sliding over the entire sector. So it's not one long slice that is sliding across. This was just what I've been doing for this animation, so it becomes clearer, but it's more smaller patches sliding across our sector. I hope that answers your question.
Thank you, Pablo. Ben Thompson raised his hand. Oh.
Yeah, okay, I can ask you. I was putting out, there's plenty of other questions there, but just an interesting thing, sort of comment, really. So really nice presentation. You looked at sort of what you could do on the receiver side. Have you also started to look what you can do on the transmit side as well and apply, so I guess, some of the similar ideas that people have been doing there for comms to this space as well?
The way you asked, I have the feeling you're asking about a particular concept. I looked into some things, or I have some ideas what we could do for the right side, which is more on making sure that the way we write our voxels is very stable. I'm not sure how much I can say, so I'm keeping it a little vague.
Yeah.
But yeah, so there's some things that we can also apply on the right side to make sure that the constellations that we actually become when looking at the read side are more crisp and more well defined, so there are fewer distortions.
Thanks.
Thank you. So Hubert from UCL has a question as well. Have you tried any other constellation shape than the circular one? And is that even physically possible?
Well, I'm not part of this team for too long, so I can't really say about what everything has been done in the past. But I guess you can answer your question easily by thinking if you could change the amount or the strength of the birefringent element. I guess you could also move, further down or further up on the Poincare sphere. So you have some control of the types of constellations that we're using. So yes, but there might be reasons for you to keep it this way.
Thank you. So we have another question from Matthew Foreman from Imperial College London. He's asking, your algorithm gives distribution that appears to be more stable. However, how well are the voxels being correctly assigned to the correct states? Or in other words, are the states of the voxel shifted to the correct region of the Poincare sphere?
So usually, I mean, in this case, they are shifted to the right point on the Poincare sphere, or they end up with the right rotation. And that's just very similar to communication systems, where you, at some point at least, at the beginning of your transmission, you will have some reference. So you might know that you will start your signal at the bottom right, and then anything else from there, you have to infer that it will be fixed to this. So you keep the tracking. Other ways to do this, I guess, are in comms differential encoding. So you don't really care about the exact position, but just about the changes. So there's, just like in optical communication systems, there are different ways to make sure that you're actually, you know, getting the right bits, even if it's not rotated the right way.
Pablo, I think though the question is more, so you managed to have, let's say, your 8 clouds, but I guess are these the corresponding bit error ratio measurement are correct, in the sense, are you really moving the point to the right cluster? I think this is, or my interpretation of the question.
That's also my interpretation of the question. I thought
okay.
I had okay. My answer was supposed to answer that question. I maybe it didn't, but
okay. Sorry,
if I should elaborate. Just let me know.
Yeah. So Hubert has from UCL has another question. Are you using any overhead data for the equalizer?
No, in this case, I think I mentioned it's the CMA, the constant modulus blind algorithm. So all it needs to know is that the expected signal is actually going to be lying on a circle, that it has a constant modulus. Anything else, so it doesn't add any overhead and therefore doesn't reduce our amount of bits that we can store in our piece of glass.
Thank you. And if you don't mind, we have another question from Heidi. Eindhoven University of Technology. So right now you're using a 2D space for your constellation during decoding S1, S2. This is a projection of your original constellation, which is in 3D, S1, S2, and S3. Would you benefit from employing 3D samples in your signal processing? For instance, if the retardance is dependent on Britten polarization?
That's a very good question. So this, at the moment, the way it does, I think you understand that it works only well because these points are very close by. So the angular deviation is very, very small. So this is why we can basically just project it onto the two-dimensional plane without having any issues. We couldn't do this if our points were more distributed on the Poincare sphere itself. But this is because I tried to point out each of these voxels are only very small or very weak birefringent elements. We would have to modify the class a lot stronger to actually create points that are, you know, distributed along the entire sphere, where if you were then to do your decision or put your decision boundaries within the Stokes space, we would have a three-dimensional constellation, and we might see some gain in just increasing the distance between our points, so would make it more robust against some types of noise. But there's always constraints to how much we can actually modify the glass. So it might be an advantage, but I think it would be limited by other practical reasons.
Thank you very much, Pablo. I don't see any further question, but if you have any further question to Pablo, don't hesitate to write it in the meeting chat and he will be very happy to answer your question. But just for in the interest of time, I would like to move on to the next talk of the event today that will be given by Arasto Sharma. Arasto is a PhD student in the photonic group at the University of Cambridge under the supervision of Professor Roger Penty and Dr. Nikos Bamiadakis. Arasto's research focuses on optics for new computer architectures and interconnects to enable high bandwidth, energy efficient on-chip intra-server and intra-rack connectivity. His talk today is about optical interconnections architecture for multi-chip system. So let's start his pre-recorded talk, and then Arasto will be live for any question that you may have. Thank you.
Hi, this is Arasto Sharma. I'm a PhD student at University of Cambridge. I'm working with Microsoft in collaboration to study optically interconnected onboard multi-chip systems. Through these slides, I will try to convey the current motivation and plans of my research project. I will be discussing the current trends in data centers and the technological shift towards optical interconnects. I will discuss the current state of the art in optical technologies and the challenges that we think are hindering us from properly exploiting these new optical technologies, especially on the system level. We make an argument that optimum use of optical network depends highly on the type of application you're running on the system. And it's necessary to see the impact of these different application traffics in our system. To conduct this exploration, we introduce a modeling methodology that captures not only the physical layer characteristics, for example, the link capacity and the energy efficiency, but also their interdependence on the link utilization of your network. In the last decades, computer systems have seen a big change. The trends of putting more and more transistors on chip is reaching a bottleneck because of the power limit, while the processor frequencies remain stagnant. All of this has led computer architects to push towards designing systems with multi-chips and multi-cores. As we shift towards multi-chip systems, there will be a need for much higher parallelization. And therefore, the bottleneck now is seen at the chip's input and output communication. There is a need for interconnect technologies with higher bandwidth, lower latency, and lower power consumption. Currently, the state of the art in electrical interconnect solutions is Intel's QPI that involves complicated SerDes and clock data recovery systems and have quite high power consumption values. Intel's white paper puts power consumption at 16.2 picojoules per bit, which is not up to the mark for future aim. Another bottleneck that copper interconnect face is scalability. As in the case of Intel's QPI, you can reach a maximum of 8 chips, that too with 2 hops, therefore causing higher latency. The reach is limited. You can reach not farther than 15 centimeters, and everything has to be very compact. So overall, electrical links suffer from problems when reaching high communication speeds. Optical interconnects have come as a solution. They perform much better in comparison to electrical links when it comes to higher bandwidth. Through the last few decades, optics has come closer and closer to the system and up to the chip level with decreasing energy consumption. Consumption has been reduced to almost 3 times better than the least possible with electrical links. Almost all the data center communication outside the rack now happens using optical fibers-based technologies. Therefore, our focus is looking inside the rack and explore optical networks on the board level. The communication that happens between chips and memories and other resources, which are the links reaching up to 1 meter length. As we start looking at the optical design space, last decade has seen a lot of solutions for devices of optical links between chips. Solutions like point-to-point systems, passive devices. The second diagram showing research from our own group. Research has shown links with much higher bandwidth, low latency, dense optical links, while energy efficiency improving by a third of electrical power. But most people just look at this as just replacing electrical links with optical links, and they haven't really considered how we benefit from their use with respect to the system. And we see, as you start to run different applications on your system network, and different applications have different link utilization according to your system, sometimes you might not see a benefit of replacing the link with optics because your power consumption has become the same. To support this point further, I would like to first look at the whole design space and optical networks on board. There has been significant research in making new optical devices and technologies, as well as studying the topology. But the impact of applications and how you allocate your resources has actually been missing. My proposition is that in order to exploit optics to the maximum, we should think of the optical design space in 4 dimensions. 2 new axes have to be added. First, the system architecture, and second, the application that you're running on your system. So we want to create a tool that captures these trade-offs and produces the performance metrics that will include the power efficiency. For optics, the power consumption changes how you utilize your link and therefore changes with the application. Second, the execution time of an application, which depends on the latency. And third, then you have to consider the implementation complexity. To explain this point, I will bring attention towards the individual parts of the design space. The first axis is the optical technology that you will use to implement your links. This diagram is a way of describing the complexity of optical links. The field is not standardized and is ever developing. There is a wide range of technology available for each part of the link. Overall, these can be simplified in 2 types of links. First, using an external laser source in which you use a modulator that modulates your bits on the wavelength you're using. This is a popular solution as it gives way to wavelength division multiplexing. You put multiple data channels in light of different wavelengths in the same optical waveguide, and this makes denser and less complex implementations. Various technologies such as silicon photonics can be used, which are easier to integrate in CMOS fabrication. Plasmonics are smaller and less energy consuming devices, but right now in research phase. Another link design could be using direct modulated lasers. VCSELs are a popular choice in this design as they provide low cost, low power consumption options. Similarly, wide range of technologies have been suggested at waveguide and receiver level. All technologies have different advantages and disadvantages. People have done a lot of research in proposing comparisons in these technologies and how they impact the bandwidth, the complexity of fabrication, and energy consumption. In this presentation, I will show a simulation that compares silicon photonic-based wavelength division multiplexing and VCSEL technologies. The other axis is the network topology, through which you determine the connections between your chips and also the chips and the memory. Networks can be point-to-point, in which everything is connected to the other. It can be a bus. It can be an actively switched system that has some arbitration. A lot of research has been done in this perspective, especially on network on chip level. The implication of this on the system is seen on scalability, as well as how much latency you have between your nodes. In this presentation, I will show a simulation that compares point-to-point and active switching topology. Coming to our own addition to the design space, there is an important axis that we are missing in the current research scope, which is the system architecture. It means thinking about what kind of resources we want to put on our board and how do our links perform as we change the application that we are running. And therefore, we can actually question if we are able to exploit the advantages of optics or not. For example, our memory resource, if we want to create more space for computing systems and use the memory resource better, research has suggested a solution could be to disaggregate your memory. Outside of the board, create a separate memory pool. But as the impact of latency is high, you will need an amount of memory closer to your chips. Now, which will depend on how memory intensive the application you're running on is. When you come to the system architecture level, you have to look at reallocating your resources to see if you're properly exploiting your network as you run different applications. The 4th dimension is looking at the impact of the applications that we run on our system architecture. And as these applications differ in how they use the architecture, for example, being more compute intensive or more memory intensive, it gives us the required perspective that we are aiming at in our study. I have shown here the 3 applications that I'm using in the simulation that we'll see further in the presentation. It can be seen that Black-Scholes is a lower data sharing application and therefore is more compute intensive. And while X264 is more memory intensive. Looking at it from a different perspective, power consumption of an optical link is the summation of static and dynamic power. And the dynamic power is the result of the packets being sent on our links. The static power in optics is constant, as you cannot shut the laser off. Therefore, if you're using a link in which communication only happens once in a while, you're wasting your power. In that case, it might be better if you had the same link as shared between different chips so that you don't waste the power. The aim now is to develop a tool that produces these performance metrics. I'm using a computer architecture simulator called GEM5. First, I design the architecture and fix the properties of each link. This simulator then loads a Linux OS in my design system and then runs a given application. I have programmed it to output network traces of communication that happen between chips, as well as chip and the memory. Also, the simulator outputs the execution time taken to run a specific application, which is one of our targeted performance metrics. The next step is to import these network traces into a device modeling tool. The tool I'm using is called Descent. Again, in Descent, I define the architecture, and using the traces, it gives us the values of overall energy per bit consumption. Now coming to the simulation, for the case of simplicity, the simulation result that I am showing, I only consider comparison in two design trade-offs, topology and technology, with different application traffic, not considering the system architecture memory allocation that we also do in our study. Starting with the network topologies, so here the comparison is made between two of these topologies. In this simulation, I'm using 4 chips on board and a shared local memory to make the comparison. First is a point-to-point system in which all the chips and the memory are connected to each other directly. As there is no switching and waiting, there is much less latency involved. In the second system, we have considered a circuit switch. All the chips have a single link that go through a circuit switch. The switch decides who is allowed to talk to whom at what time, and all the others have to wait. And therefore, there is much bigger latency involved. The first system is optimized for lower latency, as everyone is allowed to talk at all times. The links are on at all times, and therefore there's higher power consumption. The second system is optimized to perform for maximum link utilization, and therefore links are mostly only used when they need to be, without wasting power. Thus the system should have better power efficiency. The first result we get from our simulator is the execution time. The x-axis shows results for 3 different workloads with increasing data sharing with the memory. Therefore, they'll have higher utilization of link and the impact of latency becomes higher. The y-axis is the execution time of each application. This is shown in reference to the point-to-point system for each different workload. We can clearly see, as expected, that the circuit switch actually slows the system because of making the chips wait each time they want to communicate. The only problem being in the case of X264, the performance drop is quite big. The arbitration has caused larger latency, and larger latency means that the application that is dependent on latency a lot will slow down the most. The other perspective is the power consumption. The y-axis is the energy per bit shown in picojoules. The energy per bit is the division of total power consumption by the total throughput. That is the total number of bits sent through the system. The x-axis is the same. Applications are shown with increasing link utilization. Point-to-point links, shown here as P2P, were considered in 2 different technologies, one in wavelength division multiplex silicon photonics technology, and the other in 2 types of VCSEL technologies with higher number of parallel links. And as we expected, the point-to-point has higher consumption compared to the switch in almost all cases. And that is because the point-to-point link is always on, even when the link is not utilized in full. But as we run an application with higher utilization, the impact of this becomes much smaller, thus showing that in high utilization case, the drop that comes from the compute performance that from the circuit switch system is much higher than the power efficiency benefit it gives. In conclusion, your topology and technologies is very much interdependent on how you're utilizing your link. In conclusion, my argument is that as optical networks come closer to the system, the impact of system on these networks will have to be considered. And therefore, optical design space becomes a multidimensional challenge. We need a solution that looks at the problem from different perspectives and considers all aspects, including the technologies, the application traffic, and the network topology. Therefore, our aim is to quantify these design trade-offs, which will help us in designing optimal architectures functioning with high bandwidth, energy efficient optical links. Thank you.
Thank you very much, Arasto, for your very nice talk. Now the talk is open for questions. If you have any, please write it in the meeting chat or raise your hand. I would like to start also apologizing. I forgot to mention about the Microsoft supervisor, but fortunately, Arasto did do so in his first slide. Yeah, we have a question by George Zervas from UCL. He's asking, what is the scheduling arbitration method assumed or used for the circuit switching, and what is the latency overhead and distribution, medial tail during the task?
Yeah, so for this specific switch circuit that I showed, what it's doing is in Gem 5, I'm fixing, it's a router system, and which makes a table of whenever a chip wants to contact another chip, and then it takes around 4 clock cycles each time whenever it wants to contact to another chip. And therefore, this is right now I'm just fixing the latency to a specific number. From some papers, which was like 75 nanoseconds, but this can be adapted later on like depending on what type of links we have and how much arbitration we want to put in it. So that is something we control. And currently, it's just because it's just 4 different chips. It's just a simple arbitration system in which you get into a table and then you're given permission to do it. And it takes 4 clock cycles. It's fixed at that. So that's the parameter that I'm fixing in Gem 5.
Thank you, Arasto. George is following up. Do you have cases of contention and make multiple attempts?
Okay, so yeah, so depends on what type of circuit switch you're using. For the specific the simulation that I have shown, because there are only 4 chips considered here, and each chip is actually waiting for the other communication to happen because there's just single link. Because I have maximized the link utilization. So there's just single link, you have to wait for the whole time when the other chip is contacting the other. So this is not the ideal case. It's just a way of showing that in real world, you can have these type of impacts with different application if you're using this kind of switch. When we go ahead and do other types of simulation, we'll start to think about these contentions and what type of arbitration to use in the switch. So yeah, that's something to do in the future. And yeah, good point.
Thank you. I may have a question, Arasto. So you show in your application traffic simulations. What are the parameters that you are taking into account?
So these the traffic traces, I'm using computer architecture simulator called Gem 5 to produce these. What it does is that you have, so you're making connections between your core, then cache, and then the memory. So what I am doing is, so every time there's a cache hit, I ignore that connection. And whenever there's a cache miss, that means the connection, there will be a request sent to the memory now. So we take that into our trace table, and then so the information we get is the size of the packet sent, the time the packet is sent, and where the packet is sent. And then when it comes back, we again get the time it's received and the time and the size of the packet received. So that way we can understand how the link was utilized throughout the application was run on the system.
Thank you. I don't see any further question. neither in the meeting chat or don't see any raised hand. So George has a comment. Maybe prefetching can help you. But please, if you don't mind, if you have any further question, I would like to encourage you to reply on the meeting chat. I see Richard on the chat. Would you like to have any further comment?
No, thank you very much, and well done, Arasto, for your talk.
Perfect. Sorry, you appeared on the screen. Fantastic. Thank you very much for your very nice talk, Arasto. So I would like to move on to the last talk of the event today, and this will be given by Grant Brodnick and Mark Harrington. Both Mark and Grant are PhD students in the Optical Communication and Photon Integration Group at the University of California, Santa Barbara, under Professor Daniel Blumenthal. Hitesh Ballani is his Microsoft supervisor. Mark's research focuses on system integration of nonlinear resonant devices, laser stabilization, and Kerr microring solitons. Grant research instead involves integration of ultra-low loss silicon nitride photonic devices in applications that leverage narrow linewidth optical sources such as frequency and phase referencing and coherent communication. And Grant had an internship with us in 2018, working in Project Sirius, and his really focus was really the characterization of our custom tunable lasers. So today their talk will be on frequency stabilized lasers for coherent optical wavelength division multiplexing, digital signal processing free data center interconnects. So let's start the pre-recording talk, and they will be available for questions afterwards. Thank you. There is no sound at the moment. I think just please bear with us. Okay.
Everybody, my name is Grant Brodnick. I'm here today with Mark Harrington. We are students over at UC Santa Barbara and Professor Daniel Blumenthal's Optical Communications and Photonic Integration Group. We're here today to share with you Fresco. That's frequency stabilized, coherent optical, low energy, wave division multiplex DC interconnects. Before getting started, I'd like to acknowledge our funding from ARPA-E, U.S. Department of Energy, and also extend a big thank you to the folks over at Microsoft and Optics for the Cloud for having us here today so that we can join everyone in these discussions about Optics for the Cloud. So then, what is Fresco? Well, Fresco, to motivate it a little bit, maybe some folks in attendance here will be aware of the desire to move complex modulation formats into the DCI. By complex modulation formats, I mean we're encoding information both in amplitude and phase of an optical carrier, but that presents challenges because we don't have access to ideal optical carriers. We have lasers, and lasers have amplitude noise and they have phase noise, or put differently, they have a finite line width in the frequency domain. They're not a perfect delta function, right, that we can encode data onto. And what that looks like in a coherent transmission system, I'll draw your attention here to the top right. A large line width laser with phase noise will kind of blur your received symbols out if you're viewing in phase and quadrature like a received constellation. Historically, this has been overcome with digital signal processing, where you recover the full waveform of your optical signal, and then you perform mathematical algorithms to do carrier phase estimation and kind of constantly track your phase of your laser as it wanders, and untangle the data that you wrote to the phase from underneath or on top of the phase noise of your laser. However, inside of the DCI, the DSP operations may be too power intensive because of the larger transceiver count, and that motivates alternative approaches. For us, that's in the form of Fresco, where we seek to try to make a ideal optical source, right? We want to make a delta function in the frequency domain so that we can write data right on top of it. We don't have to worry about phase noise on the receiver side, but more importantly, the phase recovery electronics, if you invest in the complexity of making an ideal optical source, become simple and they become low power. So that's Fresco for DSP-free QAM and WDM in the data center. And the vision figure, a chip that I show on the bottom left here, as you can see, there's a lot of contributing teams doing different aspects of this transceiver architecture. We have narrow line width silicon photonic integrated lasers, line width narrowing and phase noise reduction stages in silicon nitride, comb generation to share this source over WDM channels in the C-band, transceivers, and as well as phase locks, and mathematics and simulations to accompany these design and motivate future Fresco architectures. So the goal of Fresco then is to enable DSP-free coherent communications in the DCI. So what have others been doing toward this same effort? Some folks show DSP hybrids or DSP-free implementations of QPSK, maybe 4 watts at 200 gig, sending an independent local oscillator over a second fiber to enable DSP-free QAM. It's a higher order modulation format. Some DSP and OPLL hybrids, where some of the efforts are offloaded to an optical phase lock loop. You have your local oscillator on the receiver side actively tracking your signal carrier in a high bandwidth, high power feedback loop. Has been shown to demonstrate some high order QAM. Your standard high bandwidth OPLLs are going toward low power as well, with some results showing integrated OPLLs with residual phase error sufficient for QPSK. But these architectures are fundamentally different than the approach we take here with Fresco. These approaches assume you have a non-ideal optical source, that's your carrier that you're writing data to, and then on your receiver side, you perform these operations to try to operate in spite of this noise. Fresco inverts the problem. We say, what if you didn't have that noise in the first place? Invest your complexity up front by approaching an ideal optical carrier, and then you offload some of the complexity and the power on the receiver side when you try to do this phase recovery. So that's the fundamental difference between Fresco and other competing approaches. And as we'll show in a little bit, it does pay off in the form of low power carrier phase recovery and higher order QAM constellations. So how do we make these nice optical sources at the chip scale for use in a Fresco architecture? Well, these low noise lasers, we employ techniques that are common in the precision, stability, and time and frequency standards community, right? So common in experiments in fundamental physics and distribution of precision frequency phase references, comparison of optical atomic clocks, for example, but applied here at the chip scale in the context of coherent communications for the first time. This line width reduction and noise reduction technique occurs in 2 stages in our system. The first stage is stimulated Brillouin scattering lasing. Without going into the physics details, I'll just say that it's a nonlinear optical process that has the effect of reducing the phase noise of your pump optical source. Reducing the phase noise equates to reducing the fundamental line width of your laser. But with a narrow fundamental line width, it can still move around or drift over time, so we engage a second high Q optical reference cavity stabilization, so an active feedback loop where we have our SBS laser track the resonance of a microcavity ultra high Q Fabry-Perot reference resonance, and that has the effect of anchoring, you know, your center frequency, your optical carrier, and reducing the total line width. Like I said, these are you know, techniques common in the fundamental physics community. Historically, the best performance is performed, you know, in tabletop scale experiments and non-integrated reference cavities. But some folks have been, you know, porting these to more compact architectures, as I show here on the right. Our collaborators over at NIST are providing the reference cavity that we use in our Fresco system here, and it's a optical microcavity chip scale to interface with our silicon nitride SBS laser pumped by a Morton Photonics narrow line width extended Bragg reflector laser. The net result and the key takeaway from this slide is that we can take a pump laser through an SBS process to reduce the fundamental line width. So that's your first stage of noise reduction. Take that SBS laser, anchor it to a high Q optical reference cavity to drive down frequency drift and total line width. And the net result is that we can have, you know, fundamental line width on the order of 1 hertz, total line width on the order of 30 hertz, at a carrier frequency of 193 terahertz, you know, C-band transmission, which is pretty remarkable. And what this is, you know, again, approaching an ideal, you know, delta function in the frequency domain for our optical carriers. And what that does, and I'll show in the next slide, is that this makes optical phase locking an easy component in the Fresco architecture, which I show here. We term the optical frequency stabilized phase lock loop, OFS-PLL. Which is fundamentally different than your standard OPLLs, which are high bandwidth, and they seek ever higher bandwidth because the higher the bandwidth, the larger line width laser noise you can tolerate. In our case, we're seeking to make this bandwidth as low as possible because we have low noise lasers. And that equates to simple electronics and low power electronics, and also very low residual phase error variance, which I'll discuss in a second here. These Fresco lasers and architectures, we achieve low residual phase error using low bandwidth electronics. You know, Mark and I in the lab even build these, you know, circuits out of op amps that we find, you know, op amps, resistors, standard stuff, less than a megahertz, and, you know, equating to milliwatts when implemented in bi-CMOS. We demonstrate this architecture here at very low received optical powers and therefore suitable for coherent communications. The system is powered by 2 stabilized SBS lasers, a TX laser and a local oscillator laser. And our local oscillator laser is tunable, and that gives us the ability to, you know, track the incoming data stream optical carrier in real time for our phase recovery. These 2 lasers to enable this architecture are mixed onto a photodiode, balanced photodiode, and you can imagine what happens if you mix 2 lasers onto a photodiode. You see the beat frequency between the 2, right? So in our case, if we're approaching, you know, narrow line width and ideal optical sources, mixing 2 delta functions, you see a nice sine wave at the intermediate frequency on an oscilloscope, and that's what I show here in the top right. So that's open loop or free running stabilized SBS lasers. And when we engage this phase lock by implementing the feedback loop and feeding back to the tunable LO, this locking error signal, the phase error signal, goes to 0, and that corresponds to a tight phase lock between these 2 optical sources. The metric that we use to determine how well this phase lock is working is residual phase error variance, and related to an optical constellation that corresponds to how much your constellation point blurs out angularly, right? So you can see that the residual phase error variance will pin what modulation order format and you're able to send, right? Your higher order modulation formats, your nearest neighbors are closer together, so it can tolerate less phase error variance. With our demonstrated phase error variance, we, in a phase noise limited link, we would be able to achieve, you know, beyond a 512 QAM a coherent transmission. So then how do we use that OFS-PLL architecture when we're sending data in a coherent data transmission demonstration? Well, the architecture is shown here. It's the same stabilized SBS, TX, and LO lasers. The phase lock portion is shown here in this box. except now we're modulating data onto the transmit laser and putting part of the signal through our coherent receiver in real-time scope to recover our constellation. So we're shooting for 16 QAM and then 32 to 50 gigabaud over 200 meters. We compare the Fresco architecture to a self-homodyne implementation, a so-called, gold standard, where your transmit laser is, split. One's the LO and one's your data. So, all the common moded phase noise should mean that phase noise recovery is trivial. So that's our highest benchmark there. And we compare it to also a standard DSP implementation, 2 independent lasers, but DSP is full tilt, frequency offset correction and tracking, and phase lock as well to recover our constellations. With Fresco and our OFS PLL running in real time, we compare it to these 2 self-homodyne and the DSP-based receiver, and show that it scales well with in comparison to these links, right? Using an error vector magnitude as our figure of merit, which is can be related to bit error rate. We show that it tracks within 1 or 2% of DSP or the gold standard homodyne, but critically, it doesn't scale with baud rate. It's just a single OFS PLL running with megahertz bandwidth feedback electronics. There's no DSP in the carrier phase recovery. This demonstrates a success of a single lambda Fresco architecture, but Fresco scales very well to WDM configurations if you can share our stable source for all C-band channels, as Mark will now discuss now.
Thanks, Grant. So now that we've demonstrated a single wavelength link, the question we have to address is how do we actually extend this to a WDM system? So while we could just use a stabilized laser for every wavelength that we need in the system, obviously a much more efficient approach would be to use an optical frequency comb to generate the source for every wavelength that we need at the same time. However, in our system, if we're to do this, we need an optical frequency comb in which each of the comb lines is as stable as our single wavelength stabilized source. But luckily, we can actually do this with a Kerr microring soliton. And the reason we can do this is that a Kerr soliton like this is pumped by a single wavelength CW laser, and the resulting comb lines typically have a very similar frequency noise properties to that of the original CW pump. So what this means is that we can, if we want a suitable low noise optical frequency comb, we can actually get that just by taking the cavity stabilized SBS laser that we've already shown working in a link and having that be input into a single silicon nitride microring resonator. And the result is an optical frequency comb in which every single comb line has approximately the same high stability and low line width of our original cavity stabilized SBS laser. So now that we've sort of described the goal here, how did we actually implement this? So the way we started here was just with an SBS laser without cavity stabilization and using that as the source of the soliton. So when we did this, we measured the frequency noise of each of the comb lines in around the first 25 comb lines around the pump at 1550 nanometers. And so what we see when we measure the frequency noise of the comb lines is that it does in fact turn out to be almost identical to the frequency noise of the pump laser. And when we compare the fundamental line width of the comb lines in this SBS laser pump soliton, which you can see here in the red, they all stay fairly close together and very close to the fundamental line width of the pump. And in this case, almost all of the deviation you see from this sort of average line is caused by the changing state of the SBS laser itself and is not actually added by the soliton. And so just as a comparison, we also took the same measurements with a tunable ECDL laser as the pump for the soliton. And as you can see, the SBS laser provides a significant advantage in terms of fundamental line width, and this advantage is clearly translated across all the comb lines in this region. So finally, we actually demonstrated our full cavity stabilized SBS laser pumping a Kerr soliton. So for comparison, this first plot in the center here shows the difference in frequency noise between just the SBS laser alone, which is what I showed in the previous slide, and the stabilized SBS laser, which is this full system. And you can see most of the improvement is in this low frequency regime under about 10 kilohertz, where the frequency improvement is quite dramatic. Now, when we move to a soliton line, what we see here is that while we retain most of this low frequency stability improvement, we do actually see some contribution of noise from the soliton generator itself. And while this, so despite this small contribution, the frequency noise and stability of these comb lines are still close enough that we can apply the same architecture principles on each of these comb lines that we could in the original single wavelength optical link. So what this means then is that we've actually successfully demonstrated an optical frequency comb with extremely stable and low line width comb lines that is suitable for use as a shared WDM source in our Fresco link. And what Grant will go into in just a minute is that this ability to use a shared source and a single stabilized laser has some fairly important advantages in terms of power consumption and system design. So back to you, Grant.
Thanks, Mark. So during lockdown, we've been busy hammering away at simulations of our Fresco architecture and energy accounting and power budgeting, primarily asking the question, how does power scale in a shared source architecture, right? And by shared source, I mean the laser and the phase locks are singular, but then they're copied out to all WDM channels, but maybe the other components such as data electronics are not. I'll draw your attention to the plot on the left where we compare the shared source scaling with a per channel coherent, right? You copy and paste all components for each transceiver to generate that second channel, whereas Fresco, our power scales well with the number of WDM channels. The Fresco power starts high, right? Because we investigate our complexity up front. That doesn't make for an energy efficient, single channel source, but it copies very well if you operate under shared source operation. As you can see, it starts high and then kind of asymptotically approaches a lower limit. As it turns out, this lower limit is set by the data electronics, right? Stuff like DACs and ADCs are major power consumers. As I show on the right here, as your number of WDM channels increases, your energy per bit gets better, but a proportionately larger amount of that energy per bit is consumed by your data electronics, ADCs and DACs, which begs certain questions and presents certain opportunities of maybe driving down future Fresco architectures by replacing those high power electronics with alternatives that are only possible if you operate in a DSP-free Fresco approach. As I'll pass it back to Mark now to discuss a little bit more about the simulation fronts that we've been doing during lockdown.
Thanks, Grant. So while we've been locked out of lab for the last couple of months, we've transitioned to developing some more sophisticated bit error rate and energy consumption models for our system. the main thrust of our bit error rate models are focusing on specifically the effects of laser noise, and most especially the effects of laser phase noise on the system as a whole. And so as a sort of demonstration of what we see with these simulations, you can see these two constellations. The left constellation is our simulation using the frequency noise properties of a relatively low noise silicon 3.5 hybrid integrated laser at a very high modulation order. And you can see with this laser, even with an OPLL, we just can't get good enough phase tracking to result in an acceptable bit error rate. No amount of reduction in OSNR will get us below FEC in this case. And as a comparison, we can see that if we use the frequency noise that results from using the same laser, but then applying our SBS and cavity stabilization process to it, we result in a link that in which the phase noise is almost invisible. And in this case, we're perfectly capable of reaching a below FEC bit error rate. And so these simulations, the second part of these simulations is to tie the results of changing the link parameters to our energy consumption. And this we can pretty easily accomplish by feeding in changes in say the received optical power of the link to the resulting penalty in OSNR and feeding it into our simulation to get a true result in terms of the actual bit error rate. And so this has sort of led us to start making some connections to additional power saving opportunities that our Fresco architecture might allow for. Specifically in this case, the obvious avenues we have for power savings is to get rid of more of the DSP that is typically, like, for example, stuff like pulse shaping, polarization, derotation, clock recovery. That's stuff that our link still uses digital signal processing for, but which is by no means required to be done by DSP. And most excitingly, actually, once we get rid of all these DSP-based components, we can start to look into stuff like reducing the bit depth of our receiver ADCs, because if we don't need DSP, at that point we don't really need high resolution information about the received waveform. Instead, we only need the level info, and we could get away with, for example, a very simple level slicer instead of a high bit depth ADC. And this could potentially result in some more significant power saving mechanisms. So yeah, in summary, we've now demonstrated a single wavelength Fresco link, and we're currently working on simulations to sort of model how we can put this single wavelength link together with our optical frequency comb version of the source to get a full WDM Fresco link. So I'd like to thank Microsoft for hosting this event, as well as everyone for listening. Grant and I will be standing by live to answer any questions you have. Thank you.
Thank you very much, Mark and Grant. I've seen a few hands raised. Paulina Babel is the first one. She's from UCL.
Hello, great talk. I was just wondering, how does the SBS laser work, and particularly what's the mechanism for line width narrowing? I didn't really catch it.
Right. So yeah, I didn't. First, thanks for the question, Paulina. I didn't go into the physics details too much during the talk, but I'll do my best here to describe it now. So SBS is a photon process. So the sequence of events goes like this. You have an optical source at sufficient intensities inside of a ring resonator, generates pressures inside of this waveguide material or clouding material. And those pressure gradients are in the form of gratings. So you can imagine these gratings also scatter photons. And when you scatter photons off these gratings that you create, those photons then beat with your incoming optical source to generate additional phonons. So now you have a gain-driven process. You have an incident optical field generating traveling gratings, generating scattered photons backward, generating additional gratings. And what happens once you set up that those dynamics is that if your pump laser frequency or phase noise causes your frequency to deviate in a really high Q cavity that we have, with a very short-lived phonon lifetime, but a long-lived photon lifetime, when your pump laser shifts, the phonons just disperse, right? So they don't remember the phase noise of the previous, configuration. What's happening though, you just have these high coherence photons that are still circulating and then beat with the pump at its new location. But that frequency that they beat at is again contributing to new phonons to generate additional gain. So it's insensitive to the phase noise of the pump, and that's how you get your line width narrowing. I'm not sure if that explanation is hopefully sufficient. It's a kind of a somewhat of a tricky process, but I'd be happy to show you some publications.
I understand about the process of SBS, but what I don't understand is the process of line width narrowing. Why should I mean you have between the pump and the Stokes there is a frequency difference. Why should the line width narrow? All previous work showed. I mean, they have shown some narrowing, but not as significant as this. What's the magnitude? What impacts the magnitude of the narrowing?
So the magnitude of the narrowing, right? Yeah. So previous work does show a line with narrowing, but ours is a little more significant, and that's because our platform doesn't guide acoustic phonons. So others try to get the Brio and gain high by doing some type of phonon engineering. Our platform, the phonon lifetime is very short, but the Q is very high, so the photon lifetime is high. So the magnitude of the line width narrowing is dependent on the ratio of your photon lifetime to phonon lifetime. So if your phonon lifetime is shorter, you get increased line width narrowing, and if your photon lifetime is higher, you again get increased line width narrowing. So with the Q of our rings around like 30 million, it's a pretty high photon lifetime with respect to phonons. So that affects the magnitude of your line width narrowing.
Okay, but with the Q as high as that, do you actually get any power out?
So we get about, I'd say 6 dBm off chip in our first order Stokes. Actually, one of the challenges we run into is that at such high Q, we generate additional orders of SBS lasing. So
yes.
Yeah, so we operate just below the second order Stokes threshold, and that corresponds to, what was that, 6 dBm, maybe 8 dBm milliwatts off chip. Mm-hmm.
At what sort of pump power?
That would be around several tens of milliwatts. So I'd say like for this particular device, I'm remembering maybe 40 milliwatts pump power, and then nearly 10 milliwatts. Sorry, that's 40 watts.
Yeah.
I'm sorry, go ahead.
Yeah, that seems high. If you could, I'd be interested to hear to see a paper on characterizing the performance of the SBS laser in such a high Q cavity, if you have one.
Oh, absolutely. So the student Surat Gunavarapu a couple years ago published these SBS laser dynamics in Nature Photonics. I'd be happy to point you to that. Its focus is specifically just subhertz lasing via line with narrowing through SBS.
Okay, because that's a critical part of this whole system, you know. So it's interesting.
Right, right. And actually, in relation to your question, there was another question about line width narrowing. See, Arslan asked.
Yeah, sorry, Grant. Could the Zishin that was first raising his hand, if you don't mind?
Oh, sure.
Zishin you from UCL. And Grant, can I ask you to copy and paste the link of the paper in the chat afterwards? Because maybe many people would be interested to understand more about your laser.
Absolutely. Yeah, I would be happy to do that.
Zishin?
Zishin asked.
I'll be happy to follow the previous discussion. Actually, I share with you. I share your view that reducing the fundamental line width is important, and making the DSP free for data center. I do see a great benefit to reduce the power consumption. One of the questions I had is I understand the phase lock loop. You can deal with the low frequency phase tracking perfectly, no problem. But I think the hard bit is the polarization tracking, which would be difficult to achieve using analog means, and my add additional power consumption as comparing to DSP approach. You have already sort of answered the question. I'm familiar with those paper you point, Joe Ken's paper you sent. Then maybe I can jump to the second question to save everybody some time. And this, I think this is also relevant to Liam's questions, which is followed as follows. How does the white frequency, white noise part scale in the frequency in your Curcom? So that's because it's a white noise, the high frequency noise that dominates, that limit your performance of the high order modulation format.
Yeah, I can actually answer that. So as far as we've measured the actual, you're essentially talking about the high frequency noise floor of the comb, right?
Yes.
And in that case, as far as we've measured and as far as we can tell from the simulation, that essentially stays the same. It's dependent on the white noise of the pump laser. Essentially, there are two contributions you get. There are two classes of contributions you get to the noise of a comb. You have noise that's from the pump laser itself, and then you have noise from the device, noise from the Kerr comb generator. And as you go to higher frequencies, any sort of effect that you're going to have from the device is likely going to tail off. Thermal effects, for example, are thermal bandwidth limited, probably to a megahertz or less at the very most. So typically, you don't really see much in the way of contribution that far out. Okay, so I should qualify this, that this is only maybe true in a fairly, this is only really true if you're fairly close to the pump laser. Once you get further out, the noise contributions from the comb start to be magnified. But this is definitely what we see in our system, and in most systems like this, where the bandwidth of the comb isn't, gigantic. It's not an octave spanning comb. It's not a giant super continuum.
It does not scale with the number of combs. When you go to the outside of the comb, it does not scale.
No, not at our operating point. This is not always the case, but I mean, we have a fairly low line width laser, obviously, and it's still not the case. Because in our case, yeah, the white noise of these, at least if you're talking about the white noise of the comb lines themselves, they're dependent on the pump laser.
Okay, then my relevant question is, what's the integration range when you calculate the line width?
So and we didn't go into this in too much detail. There were essentially two relevant ways we did integral line width. One was it's something called you integrate from essentially as far out as you went in your frequency noise measurement up until you get to, I think, 1/pi. And that gives you a sort of estimate of a sort of like a white.
What's the range you use? What's the?
So we typically measure frequency noise out to around 5 megahertz, and to about 1 kilohertz in measurements I showed, and for the better lasers down to about 1 hertz.
Yeah. Clear. Thanks.
Okay.
Thank you.
Okay, thank you. If you don't mind, we move on to the next questions. We have quite a few. Arslan from EPFL is asking if the initial lasers that you need to start with has to be a ultra low noise laser, line width laser.
Right. So for these results that we showed here, it was the external cavity Morton photonics laser, as you pointed out, Arslan. We recently showed results at Clio of the SBS process line with narrowing using silicon photonic 3.5 integrated lasers. And we showed line with narrowing, I think, from the order of a kilohertz or a few down to several hertz. So you definitely get, it's a narrowing of the pump source. So if you have a better pump source, your output laser is going to be better. But certainly with the magnitude of line with narrowing that we're able to do in this silicon nitride platform, you can get away with using integrated lasers. So that's actually part of the Fresco. One of the Fresco thrusts is design of these on-chip pump sources to pump the silicon nitride lasers, so we can start to move away from ECDLs and the other table scale lasers. Mm-hmm.
Yeah, the line width narrowing effect is on the order of a couple hundred, maybe around 400, I think. So that's about, if you have a really low noise laser like a Morton laser, you end up being limited by the thermal SBS noise. But if you use a noisier laser, you end up being limited by the actual line width enhancement factor, which is, or it's maybe not the right term to use, but that's around 400 or so in this device, I believe.
Okay, thank you. Maybe you will be able to take only a couple more questions, and if you don't mind to try to be concise in the answer, as there are lots of questions. So the next one is from Ronit Sohampal. The question is, how sensitive is the Soliton microcomb to temperature fluctuations, and would these lead to any significant issue with comb line phase stability?
Yeah, so I can talk about this a little bit. One of the advantages, and you're probably aware of this, of these types of Soliton platforms, is that they're thermally self-locked. So in general, if the temperature fluctuations are on a relatively slow time scale, the Soliton itself will stay locked, and since the actual noise contribution of the ring itself is not very large, this doesn't really tend to lead to very large effects on the actual stability of the comb. Essentially, what you would be doing is you would be modifying the detuning that you're operating at slightly, which will modify the spacing of the comb. And so that will show up as, like, say, a frequency noise fluctuation, but it'll be on a very low frequency because it's this thermal fluctuation. It's definitely, I would say it's definitely more of a long-term stabilization issue than a noise issue. It won't add that much noise, but it does cause problems, keeping your Soliton in its operating mode. But yeah, it's good.
Thank you. I believe the question to Liam Barry was answered, but please, Liam, raise your hand if this is not the case. No. Then the last question is from Tom Gerard from UCL. He is asking, can you please comment on the importance of serialization for achieving the QAM in the Fresco link? These are often quoted as being too power hungry and large for on-chip advanced modulation.
Yeah, that's a great question. It's not necessarily my area of expertise. I don't actually know if I have a good answer for that. Right now, Fresco's in the stages of eliminating certain architectures for DSP. So I don't know if we can get rid of serialization necessarily. So that might have to stay. And whether that makes it too power hungry for on-chip advanced modulation, I guess we'll have to see. Maybe at some point it'll be worth where people are willing to take that hit and still use advanced modulation so they can get higher spectral efficiency. But I don't actually have a solid answer, sorry. Mark, do you have anything to
add? Not to that. There's another follow-up question, which if we have time for, on the fill and gain in cone dimension devices. I'm not sure if we have time for that, but I want to make sure that I get this. I'll answer it in the comments if we don't.
If you don't mind, sorry, I didn't pick Arslan as he had already one question, but if you wouldn't mind, I was about to ask, thank you for raising it. If you wouldn't mind to answer in the meeting chat, whatever we didn't have the chance to answer, I just would like to close it down. Thank you so much, both of you, Mark and Grant, for the very nice talk and following discussion. It was it was great. So I would like to pass over to Ant. If Ant wouldn't mind, I just would like to thank you all for taking part at our event. It was my first time chairing a virtual event, so I had a fabulous time, and I just would like to thank you all. So Ant, over to you. Thank you.
Yes, well, I mean, it's a great pleasure to wrap this event up. It's been a fantastic 2 afternoons. I'd also like to echo Francesca's comments there, and I'd like to thank all the speakers. I think it's incredibly hard sometimes to give these talks online, and I think you all did incredibly well. Both the recorded and the live ones I thought were fantastic. So I'm actually going to suggest that we all unmute and just give the speakers a round of applause in reality. So can I ask everyone to unmute and then give a round of applause? Thank you very much. And then if you could mute again so we don't get any of these feedback loops, that would be fantastic. One of the things I thought as I heard all these talks is not only are they fantastic pieces of work in their own right, but there's a lot of overlap. There's a lot of things where there's connections between these talks. And I would encourage both the PhD students and their supervisors to encourage the students to reach out to each other. If you've seen a talk during the last 2 days where you think that's quite related or that's got an overlap with what I'm doing, I would encourage you to reach out. I think one of the reasons we set this up was to encourage collaboration with us, but also collaboration with other people. And this is a great opportunity. And I know it's always easier if it's in person and you can grab them, and we'd be having some canopies or some bottle of beer or something now, but we won't. But that doesn't stop you from reaching out just to people and saying, hey, I liked your talk, it related to my talk, can we talk a little bit more? I'd also like to just thank a few more people. I'd like to thank Francesco, who I think has done a great job chairing the sessions. I'll give you a solo. Everyone's joining in with me. I want to just and the sort of both on the technical side and the non-technical side, and Scarlett and Claire and Lynn for making sure this meeting has gone extremely well, both the online part and the ramp up to it and everything else and the planning. Thank you very much. Another round of applause. So before I sort of thank everyone else for coming, I just wanted to ask and throw the floor open in case there was any comments or feedback or anything that anyone else would like to provide. Formal feedback, we'll send out some form, I think, which will capture some of it. But is there anything that anyone else would like to share or would like to add at this stage? Going, gone. Okay. So in that case, I'd like to just wrap up by thanking all of the attendees. I know, we've got some folk in UCSB, so they're, whatever it is at the moment, 8 o'clock in the morning, 7 o'clock in the morning, 6 o'clock in the morning, I'm not quite sure what it is, but thank you for joining us. Thank you for those in Europe for joining us. As a virtual event, I think it's been fantastic. And part of that has been the questions, the interaction that has happened. And that is down to you and people really participating and listening during the time. So thank you very much. So a round of applause to all you as well. So I think that's it. Scarlett, is there anything that I have forgotten to say or do at the end?
No, the only thing is that we will send the form around. That should be in the chat window, the link, and we'll also follow up by email. But yes, we are in there potentially into virtual events for quite some time to come. So we are really interested in your feedback and how we can improve it further.
Really, yes. I have a feeling there'll be many more virtual events over the next 12 months. Okay, thank you, everyone. That's it. End of workshop.
Thank you.
Bye.
Thank you very much.
Thank you.
Bye,
Bye.
everybody.
Bye.
Bye.
Bye.